The largest unreinforced concrete dome in the world is on the Pantheon. It's not a modern marvel, but rather an ancient Roman temple built almost 2,000 years ago. So if concrete structures from the Western Roman Empire can last for thousands of years, why does modern infrastructure look like this after only a couple of decades? Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're taking a look at the factors that affect design life of concrete. This video is sponsored by Brilliant. More on that later. If you haven't seen the previous videos in this series about concrete, here's a quick synopsis. We've talked about how concrete's made, why it often needs reinforcement, and how that reinforcement can sometimes lead to deterioration. Concrete reinforced with steel bars is the foundation of our modern society. The reinforcement is required to give the concrete strength against tensile stress. We use steel as reinforcement because of its strength, its similar thermal behavior, its availability, and low cost. But steel has an important weakness: it rusts. Not only does this corrosion reduce the strength of the reinforcement itself, but its byproduct, iron oxide, expands. This expansion creates stresses in the concrete that lead to cracking, spalling, and eventually the complete loss of serviceability, i.e. failure. In fact, corrosion of embedded steel reinforcement is the most common form of concrete deterioration. But it hasn't always been that way. The Romans got around this problem in a very clever way. They just didn't put steel in their concrete. Simple enough, right? They harnessed the power of a few clever structural engineering tricks like the arch and the dome to make sure that their concrete was always resisting compression and never tension, minimizing the need for reinforcement. One of those clever tricks was just making their structures massive, and I mean that literally because the simplest way to keep concrete in compression is to put heavy stuff on top of it. For example, more concrete. We use this trick in the modern age as well. Most large concrete dams are gravity or arch structures that rely on their own weight and geometry for stability. In both gravity and arch dams, the shape of the structures are carefully designed to withstand the water pressure using their own weight. You can see how they get larger the deeper you go. So even with the tremendous pressure of water behind the structure, there are no tensile stresses in the concrete, and thus no need for reinforcement. But lack of steel reinforcement isn't the only potential reason that Roman concrete structures have lasted for so long. Another commonly cited suggestion for the supremacy of Roman concrete is its chemistry. Maybe they just had a better recipe for their concrete that somehow got lost over time, and now those of us in the modern era are fated to live with substandard infrastructure. In fact, in 2017, scientists found that indeed the combination of seawater and volcanic ash used in ancient Roman concrete structures can create extremely durable minerals that aren't normally found in modern concrete. But that's not to say that we can't make resilient concrete in this modern age. In fact, the science of concrete recipes, also known as mixed design, has advanced to levels a Roman engineer could only dream of. One of the most basic, but also most important factors in concrete's chemistry is the ratio of water to cement. I did an experiment in a previous video that showed how concrete's strength goes down as you add more water. Extra water dilutes the cement paste in the mix and weakens the concrete as it cures. The Romans knew about the importance of this water to cement ratio. In historical manuscripts, Roman architects describe their process of mixing concrete to have as little water as possible and then pounding it into place using special tamping tools. Interestingly enough, we have a modern process that closely mimics that of the ancient Romans. Roller compacted concrete uses similar ingredients to conventional concrete, but with much less water, creating a very dry mix. Rather than flowing into place like a liquid, RCC is handled using earth-moving equipment, then compacted into place using vibratory rollers like pavement. RCC mixes also usually include ash, another similarity to Roman concrete. It's a very common construction material for large gravity and arch dams because of its high strength and low cost. Again, these are usually unreinforced structures that rely on their weight and geometry for strength. But not everything can be so massive that it doesn't experience any tensile stress. Modern structures like highway overpasses and skyscrapers would be impossible without reinforcing the concrete. So generally, we like our concrete to be more viscous or soupy. It's easier to work with. It flows through pumps and into the complex formwork and around the reinforcement so much more easily. So one way we get around this water content problem in the modern age is through chemical admixtures, special substances that can be added to a concrete mix to affect its properties. Water-reducing admixtures, sometimes called superplasticizers, decrease the viscosity of the concrete mix. This allows concrete to remain workable with much lower water content, avoiding dilution of the cement so that the concrete can cure much stronger. I mixed up 3 batches of concrete to demonstrate how this works. In this first one, I'm using the recommended amount of water for a standard mix. Notice how the concrete flows nicely into the mold without much need for agitation or compaction. After a week of curing, I put the sample under the hydraulic press to see how much pressure it can withstand before breaking. This is a fairly standard test for concrete strength, but I'm not running a testing lab in my garage, so take these numbers with a grain of salt. The sample breaks at around 2000 psi, or 14 megapascals, a relatively average compressive strength for 7-day-old concrete. For the next batch, I added a lot less water. You can see that the mix is much less workable. It doesn't flow at all. It takes a lot of work to compact it into the mold. However, after a week of curing, the sample is much stronger than the first mix. It didn't break until I almost maxed out my press at 3000 psi, or 21 megapascals. For this final batch, I used the exact same amount of water as the previous mix. You can see it doesn't flow at all. It would be impossible to use this in any complicated formwork or around reinforcement. But watch what happens when I add the superplasticizer. Just a tiny amount of this powder is all it takes, and all of a sudden, the concrete flows easily in my hand. In many cases, you can get a workable concrete mix with 25% less water using chemical admixtures. But most importantly, under the press, this sample held just as much force as batch 2, despite being just as viscous as batch 1. The miracle of modern chemistry has given us a wide variety of admixtures like superplasticizers to improve the characteristics of concrete beyond a Roman engineer's wildest dreams. So why does it seem that our concrete doesn't last nearly as long as it should? It's a complicated question, but one answer is economics. There's a famous quote that says anyone can design a bridge that stands, but it takes an engineer to design one that barely stands. Just like the sculptor's job is to chip away all the parts of the marble that don't look like the subject, a structural engineer's job is to take away all the extraneous parts of a structure that aren't necessary to meet the design requirements. And lifespan is just one of the many criteria engineers must consider when designing concrete structures. Most infrastructure is paid for by taxes, and the cost of building to Roman standards is rarely impossible, but often beyond what the public would consider reasonable. But as we discussed, the technology of concrete continues to advance. Maybe today's concrete will outlast that of the Romans. We'll have to wait 2,000 years before we know for sure. Thank you for watching, and let me know what you think. Thanks to Brilliant for sponsoring this video. In my career as a civil engineer, I'm constantly on the lookout for new ways to do my job better, and often that means learning new skills. Recently, I've been using Brilliant to brush up on my understanding of probability. Civil engineers work on projects that can last many years, so for me, being able to anticipate risks and estimate their probability has helped me get ahead at work. Brilliant starts you with the fundamentals and provides interesting exercises and puzzles to help you master each concept at your own pace. I find that I learn best when I can apply the skills immediately, so I love the interactive problems you can work in each lesson. To support this channel, go to brilliant.org/practicalengineering and sign up for free. The first 200 people will get 20% off the annual premium subscription. Again, thank you for watching, and let me know what you think.